My name is Ron Lifshitz. I'm from Tel Aviv University, and it's my pleasure to open the second day of this exciting meeting. We have two talks in this session. The first talk will be given by Jean-Marc Triscone. Looking over his CV, it seems that he managed to be completely loyal to the University of Geneva since the first days of becoming an undergraduate student. Apart from a couple of short-term visits, he's been there for his whole career, climbing up to the position of vice rector. He's also recipient of a number of prestigious prizes, and many of them are associated with his involvement in the discovery of superconductivity at these Oxide interfaces, so it's a pleasure to have him here.
Thank you very much. So thank you very much, and let me also start by thanking the organizers for the invitation. It's a pleasure for me to be here and to be able to tell you about some of our activities on oxide structures and oxide interfaces. In this presentation, I will mainly discuss the lanthanum aluminate strontium titanate system, or LaO STO, and I will discuss superconductivity in detail. Now, since it's a school, I will also mention some other aspects of the system, and I will also try to motivate this research and explain why we believe that this field is an interesting field of research. So the system I will focus on is the interface between two good band insulators, strontium titanate and lanthanum aluminate, which have relatively large band gaps. And it was found in 2004 that if you start with a single crystal of strontium titanate in the 001 direction, and if the single crystal is terminated by a plane of titanium dioxide, which you see here, and you grow on this single crystal an epitaxial layer of lanthanum aluminate, you find at the interface between these two good insulators, you find a conducting layer. And you see here the sheet resistance versus temperature. This system is metallic and has a large mobility. And what you see here is a sample which is perfectly transparent, but you see our electrodes to contact this conducting layer and to measure its properties. And the stunning discovery of Akira Otomo and Harold Wong with us today generated a lot of interest. And you see in the back of the slide some of the papers which have been published on this subject. And I think the interest for the system, there are different interests. One, we would like to understand why is the interface between two insulators conducting. This is one thing. And the other thing is that we have in the system mobile electrons in a complex oxide. And so we can hope for interesting properties. In 2007, in collaboration with Johan Mannhardt and his team, we discovered that this interface is also superconducting. You see here, again, the sheet resistance versus temperature, and you see the superconducting transition with a low critical temperature of about 250 millikelvin. And after this work, there were several reports of magnetism at this interface using different techniques, signatures in transport, in torque experiments, or using scanning squid. I will not discuss magnetism in my talk, but you will have on Wednesday a talk of Bina Kaliskish. I think she will talk about domains in strontium titanate, but maybe you will also address some issues about magnetism. After all this work, at the end of 2007, in Science magazine classified these discoveries as one of the breakthrough of the year. And I'm mentioning this because in the Science magazine you could see this question, beyond silicon, can we go with this system beyond silicon? And what I will try is to come back to this question at the end of my presentation. So what I would like to do is start by explaining why we're interested in these oxide interfaces. I will discuss or mention the origin of conductivity, or explain at least some of the ideas. Then I will move to superconductivity, and I will show you that this system is quite special. One is able in the system to control superconductivity using an electric field, very much like in using a transistor-like structure, and this is quite unique. Then I will move to things which are which reflect more recent work, where we did try to compare this interfacial superconductivity with superconductivity that you find in bulk doped strontium titanate. And as you will see, there are some surprises. Yes. And if time allows, I will also discuss recent measurements in this more complex systems that I will introduce. And at the end, I will just flash some developments and some recent studies on the system. Okay, so why are we so interested in oxide structures and oxide interfaces? And maybe one of the first things to say is that oxides display a variety of electronic properties. And if you focus here on the perovskite structure with a simple ABO3 formula, with the A cation in the corner, the B in the center, and this oxygen octahedra, one is finding that depending on the choice you make for the A and B cations, the properties are completely different. So you can have perovskites which are insulating or which are conducting, but maybe more interestingly, these perovskites display a variety of instabilities. So some of these instabilities are structural. They can be antiferro distortions, so like here, rotations of oxygen octahedra that you find at low temperature, for instance, in strontium titanate. You have polar instabilities, which lead to ferroelectricity. This is what you find in barium titanate. And you can have electronic instabilities leading to orbital order, magnetism, or superconductivity. And all these properties are found within the same family of materials. We also know that many perovskites display strong correlations and complex phase diagram. I'm just flashing here two examples. This is a phase diagram here of manganites, temperature doping, of cuprates. And the only thing I want to show is that when you look at this phase diagram, you see very many phases. And these phases are telling us that you have different states in these systems which are probably very close in energy. In some sense, a system has difficulties to choose its ground state. And this is why these materials are very sensitive to external parameters like pressure or magnetic field. And sometimes it's enough to modify slightly the environment to allow for a phase change. This is also why one is believing that these materials are probably very good materials for sensors, because eventually a small stimulus can lead to a large response. Now, I just said that these materials are belonging to the same family. And so it's a little bit like a Lego bricks that one can eventually pile up very precisely. And you see here examples of lead titanate and strontium titanate, and you see that the lattice parameters are also very similar. So today we have different techniques which allow epitaxial growth of these compounds to be made, and beautiful structures and very perfect structures to be realized. And you see here the interface between strontium titanate and lanthanum aluminate. And these techniques include pulse laser deposition, sputtering, molecular beam epitaxy. And I think it's fair to say today that if you compare 3-5 structures with oxide structures, the level of quality of the oxide is really becoming better and better. Now, I said just before that these materials are quite sensitive to perturbations. You have different states which are close to energy. Now, if you think about an interface, and you see here the interface, an interface is a major perturbation because you've changed half of the neighbors. And so on general ground, one can imagine that this interface may produce new effects. And if you think about the fundamental symmetry breaking, which is taking place at an interface, maybe strain gradients, charge transfer, frustration, or eventually electrostatic coupling, you realize that at interfaces, we may obtain properties which are different from the materials which are involved in this interface. And the idea is that in oxides, where you have many degrees of freedom, charge, spin, orbital, lattice, that this interface will eventually lead to new functionality. So this is a dream of this field of research, which is to use oxide interfaces and ideally find new properties, new functionalities. Okay, so let me now move to the LaO-STO system, and I would like first to mention the persons in Geneva who are involved in this work. Stefano Garilio is a permanent member in the group who is following very closely all this development. Alexandre Fett just finished his PhD. Denver Lee and Margarita Boselli are PhD students, and Willie Yu was a postdoc in the group. She's just back in the US. And I would like also to mention very important former members who participated to the early days of this research on LaO-STO. André Caviglia is now an assistant professor in Delft. Nicolas Herran joined CNRS in Paris. He's working in the group of Albert Fert. Claudia Cancelleri, she's now at EMPA, close to Zurich. And Daniela Stornaiolo is now in Naples. And I would like also to mention a very important collaboration with Marc Gabet, who's a theorist at the University of Paris Sud, and Marc has been extremely important to help us understand the properties of this system, and also long-standing collaboration with Johan Mannert. Just one slide on how one is preparing these interfaces. I can obviously answer questions, but I will not discuss this in great detail. What we do, we start with a single crystal of strontium titanate, 001, which is TiO2 terminated, and we grow using pulse laser deposition a layer, a very thin layer of lanthanum aluminate. Typically, we use 800 degrees C in some partial pressure of oxygen. Now, what is important is that when you heat strontium titanate, very often you generate oxygen vacancies. And so to avoid as much as possible oxygen vacancies, we introduce, after the deposition at high temperature, 200 millibar, very high pressure of oxygen, and we let the sample cool in oxygen. And this is maybe a little bit technical, but it allows a very good reproducibility, but from samples to samples, from sample to sample to be obtained. When we grow this lanthanum aluminate layer, we use a technique which is called read, which allows the layer by layer growth to be followed, and which also allows the thickness to be very precisely measured. And when you end the deposition, you can use atomic force microscopy technique to look at the surface. You see step and terraces, which mimic the structure of your substrate. You find for relatively thick films these additional fringes on X-ray diffractograms, which allow you to check that the thickness of the lanthanum aluminate layer that you got from the read is indeed the correct one, and you can also do some TEM to check the surface, the interface quality. Okay, so let me move now to the origin of this conduction, and it's been proposed from the beginning by Harold and co-workers that this conduction may be linked to a polar discontinuity that you find at the interface. And this is a so-called polar catastrophe scenario, which in fact is quite simple to understand. If you look at strontium titanate in the 001 direction, you alternate planes of strontium oxide and titanium dioxide. These planes are neutral planes. Strontium is 2+, oxygen is 2-, so this is a neutral plane. But when you move to lanthanum aluminate, lanthanum is 3+, and so this plane as a formal charge, +1, -1, +1, -1. Now, if you think about infinite capacitors, you know that in an infinite capacitor, the electric field is confined between the planes. And so what you have here is an electric field between this layer and this one, and you have an electric field between this layer and this one. Now, if you think in terms of potential, you realize that when you start growing your lanthanum aluminate layer, so you have these electric fields I was mentioning, and you see that the potential is growing as you increase the thickness of the lanthanum aluminate. And this is this polar catastrophe. Now, at some point, the system has to do something, and one possibility is to transfer from the surface to the interface half an electron per unit cell. And if you do this, then the potential is not anymore diverging, but is oscillating around 0. And these electrons can go in the titanium 3D band. And if you make a calculation, you find that the sheet carrier density, so this is quite important, this is the density of carriers per unit area, is 3×10⁻14 per square centimeter. I will come back to this. This polar discontinuity problem is a well-known problem, and it happens in many systems, like in this gallium arsenide germanium system. But there, the system will work out on an atomic reconstruction to avoid this diverging potential. What is different in the system is that titanium is a transition metal oxides, which can have different valences. And so in strontium titanate, titanium is 4+, but titanium can be also D0, no electrons in the D band, but you can have electrons in the D band, and this is what happens when you transfer these charges. Now, other scenarios have been discussed a lot, in fact. The possibility that lanthanum-strontium intermixing at the interface is playing a role, and in fact we have some intermixing. This is again a paper of Harold Wang and co-workers. Oxygen vacancies have been discussed a lot, because one knows that in strontium titanate it's quite easy to generate oxygen vacancies. Maybe one thing to say is that these scenarios can bring conduction, but they do not solve the polar catastrophe problem. Because to solve this problem without off-stoichiometry, we really have to transfer charges from one side of this capacitor quotation mark to the other side. Okay, let me discuss now a bit in more detail this interfacial structure. This is a band structure at the interface. Strontium titanate with a 3.2 eV band gap. Lanthanum aluminate, 5.6 eV. There is a small shift here. And now, because you have this electric field in lanthanum aluminate, you have band bending. And you see that the top of the valence band of LaO is going up in energy with the thickness of lanthanum aluminate. And at some thickness, you reach the bottom of the conduction band of STO. And here, you can have a Zener breakdown, and you can transfer charges from the top to the interface. So what it means that this model predicts that if the thickness of lanthanum aluminate is below this thickness, the system should be insulating, and above it should be conducting. It is very easy to calculate this critical thickness, because we know the surface charge. You know that in a capacitor, the electric field is simply the surface charge divided by the dielectric constant of the material and the vacuum dielectric constant. So you can calculate the electric field. We know this distance in energy or in volt, and so you can calculate the critical thickness. So this is really a one-line calculation, and if you do this calculation, you find that the critical thickness is 3.5 unit cells. So the prediction is simple. Below 4 unit cells, the system should be insulating, and it should be conducting above. And this was observed first in the group of Joren Mannert. You see here the results. Conductance versus lanthanum aluminate thickness in unit cell, 1, 2, 3, insulating, 4 unit cell conducting. and you see all these some points measured in Geneva. This is a very robust result, which has been, and this has been observed in at least 5 or 6 groups. Now, a few years ago, with colleagues at PSI, we decided to further test this polar catastrophe scenario. And the idea was, can we tune the level of the polar discontinuity and check the prediction for the critical thickness? And what we did was, in fact, quite simple. We replaced lanthanum aluminate by an alloy of lanthanum aluminate and strontium titanate. And if you take 50-50, you realize quickly that instead of having +1 -1, you will have +1/2 -1/2. So you lower the level of the discontinuity. Now, it turns out that in this alloy, the dielectric constant is the same as the one of lanthanum aluminate, about 23. And so the only thing which is changing here is the electric field, which decreases by a factor of 2. But now if you think about it, if the electric field is decreasing by a factor of 2, then the critical thickness should double. And this is indeed what we see. This is a sheet conductance versus film thickness. This is lanthanum aluminate. This is a step I was just discussing. And if you look at this 0.5 alloy, you see that this critical thickness is shifted maybe to 7 unit cells. So experiments which are in line with this polar catastrophe model. Let me end by mentioning that there is a lot of ongoing work on this. There is a lot of ongoing work on the mechanism, and there has been recent work by Bristov and co-workers, Yu and Zunger, and Zhu and co-workers. And all these models still rely on the polar discontinuity at the interface. But the explanation for the conductivity is different. And here the idea is that what will happen at a critical thickness is that the formation energy of oxygen vacancies, not in STO, but at the surface of the lanthanum aluminate, will reach 0. And the calculations show that it's precisely at 4 unit cell. So at 4 unit cell, you start forming these vacancies at the lanthanum aluminate surface, and each vacancy is freeing 2 electrons. And these 2 electrons flow to the interface and give rise to conduction. So very interesting models, but I will not discuss this in detail. Okay, now let me move to the electronic structure of the system. And the first question is, we have this conducting layer, and the question is, what is the thickness of this conducting layer? And as you will see, the thickness and the confining potential will be very important to determine the electronic structure of the system. So how do we measure the thickness of this conducting layer? Different techniques have been used. Here in Paris, what they did, they made a cross-section of a sample, and then they came with an atomic force microscope equipped with a metallic tip, and they just measure the local conductivity. And you see these conductivity maps. This is room temperature, this is low temperature, this is strontium titanate, lanthanum aluminate, and you see here at the interface the conducting layer. And you see that at low temperature, the conducting layer expands. This is due to the dielectric constant of strontium titanate, which is diverging as we go to low T. Strontium titanate is nearly ferroelectric. And the thickness which was measured was about 12 nanometer. In Fribourg, in the group of Christian Bernard, they use optical spectroscopy, and they were looking at a mode which is confined by the width of the conducting layer, Berman mode. And from this analysis, they could extract a profile for the carriers. And again, they find something around 11 nanometer at low T. In Geneva, we use superconductivity to determine the thickness of the superconducting layer. And I will explain this because I will need this a little bit later. So what we do, we measure the superconducting transitions in perpendicular and in parallel fields. So once the field is perpendicular to the interface, and in the other case, it is parallel to the interface. And you see here the transitions. This is the perpendicular direction, parallel direction. It looks very similar, but in fact there is a large anisotropy. You see here that 100 millitesla is nearly suppressing superconductivity. In the parallel case, 100 millitesla does not do very much, and you need maybe 2 Tesla to destroy superconductivity. Now, if you have this data, you can determine TC by choosing a criterion, for instance, a 50%. You take the temperature at which the resistance drops by 50%, and this is giving you the TC for a given magnetic field. And now with this data, you can trace the critical field. So this is critical field versus temperature. This is the perpendicular direction and the parallel direction. For the perpendicular direction, you can extract, using this formula, the in-plane superconducting current length, which is maybe 60 nanometer or 70 nanometer, depending on the sample. And now for the specialist, when you see the square root of T behavior, you know that you're measuring a thin layer. This is a signature of a thin layer. And from this formula, which relates the parallel critical field to the in-plane current length that you know from the analysis of this curve, you can extract the thickness of the superconducting layer, again, about 10 nanometer. And I will use this technique a little later, and I will explain why. OK, so we have a layer, a conducting layer, which is confined within a distance of about 10 nanometer. And there are 2 consequences. The first one is that this confinement is lifting the degeneracy of the T2G orbitals. In a perovskite structure, if you look at the D band, you have the T2G orbitals and the EG orbitals. The EG are pushed at much higher energies by crystal field splitting. And this is simply due to the fact that the lobes for the EG orbitals are pointing towards the oxygen, and so this is more costly in energy. In a cubic structure, the T2G are degenerate. But here, the XY orbital, which is parallel to the interface and which allows easy conduction, is lower in energy. And this splitting, which is here, was first observed by Marco Saluzzo and co-workers experimentally. And you see here calculations, electronic structure calculation, which shows that because of this confinement, you start to produce subbands. And you see here 1, 2, 3 XY subbands, so light bands. And then only at some point you start to see the XZ and YZ and XZ heavier bands. And this will be important a little later. Now, if you look now in space to the extension of these different electronic bands, you see here lanthanum aluminate. This is strontium titanate. This is energy. And you see here now the wave function square. For the lowest one, you see here that these electrons are very localized spatially at the interface. And you see that when you move up in energy, the electrons are going deeper and deeper, and the XZ, YZ are going deeper than the XY. You also see that the probability to find electrons is localized on the titanium. So it is quite different from a 3-5 electron gas, where you would find some envelope function. And this is why we call this system, we prefer to call this system a 2D electron liquid than a 2D electron gas. OK, so let's keep this in mind. It will be important for the discussion of superconductivity. OK, let me move now to transport experiment. So this is your system. I told you it's metallic. If you measure the whole response and you extract some information on the carrier density, you find that the mobile carriers density is 2 to 8, 10 to the 13 per square centimeter. Again, what we measure is the sheet carrier density, so the carrier density per square centimeter. Now, maybe you remember that I told you that the polar catastrophe scenario was predicting 310 to the 14. And so here, we have 1 order of magnitude lower mobile carrier density. So we're not completely sure about this. We believe that the electrons are transferred, but maybe many of these electrons are trapped at the interface. And the mobile carrier density we see here is only 2 to 8, 10 to the 13. Now, this is a very low carrier density. If you think about it, it's 1 electron every 25 unit cell looking from the top, and these electrons are spreading over several nanometers. Now, if you think about this, and if you look at our structure with our electron liquid, which is here, between two insulators, this is an ideal situation to perform field effect experiment, because your gate dielectric is already there. You can either use lanthanum aluminate or you can use strontium titanate. And this is indeed what we did. And many groups have been exploring field effect with the system. And what you can do, you can use your strontium titanate crystal as a gate dielectric. So you put a gate on the back side. The strontium titanate crystal is thick, typically 0.5 millimeter, which means you will have to put quite a large gate, but it's in fact quite convenient. You can also put your gate on top of lanthanum aluminate, or you can even use side gates like here. And this is a side gate experiment where we see the change in conductance as a function of a few volts, and you see the very large effect. Now the question is, you can perform this field effect experiment, you can tune the carrier density. What will happen to superconductivity? I'm showing this on this slide. So this is a curve measured with 0 volt applied. We have a back gate in this configuration, so on the back side of strontium titanate. And then I'm reducing the carrier density. And if you reduce the carrier density, you see that the resistance is going up, which makes sense. Here TC is going up a little bit, but then TC is going down, and you see that you lose superconductivity. Now, what we have here is a superconducting switch, which allows the on-off switching of superconductivity. And in fact, this is something very difficult. We've been working many, many years on different systems to try, including high TC, to try using an electric field and controlling superconductivity. And this is really something which is quite unique in the system, that you can go back and forth at low T between these two states. Now, you may have seen recent work on cuprates and strontium titanate using the ionic liquid technique, which allows a huge amount of carriers to be induced or removed. And this EDLT technique indeed allows on-off switching of superconductivity. The difference is that to change the applied gate, you have to go back to room temperature, because you have to be above the freezing temperature of your ionic liquid. So this is a beautiful switch. You see here another experiment we perform with Johan Mannert with a top gate. And you see here that the resistance is 0 for 1.5 volts. You go to 0 applied bias. The system is in a dissipative state, and you can go back and forth. OK, so we measured many of these curves and many samples. And this is in general what you see. This is the sheet resistance versus temperature, log scale, linear scale. You see that you lose superconductivity, and you move to a state which is not a very good insulator. You see here the resistance is increasing, but maybe even saturates. OK, with this, you can define again a TC. And now you can plot TC versus the gate voltage. And this is what you see here with the superconducting pocket. By the way, I wrote 2D superconductor because I forgot to mention before. But when the Coherence length, the superconducting Coherence length, is larger than the thickness, your system is 2D. Now, when we saw this at the time, we tried to look at the dependence of TC close to this quantum critical point. And we saw that TC was going as the voltage minus the critical voltage, which is here. It could be carrier density. It's linear in this regime, to a power 2/3. And 2/3 is the exponent product you expect for a 2 + 1 dxy quantum phase transition. And when we saw this, the xy model is a phase model. So we wonder if this was telling us that the zero resistance state is here controlled by the locking of the phase. So in other words, that you have phase fluctuations here in this system. And I will come back to this a little later. That may seem strange at very low T, but the carrier density is extremely low. So the superfluid stiffness is also extremely low. Okay, before to continue with superconductivity, let me mention one more thing which is important, which is also linked to the breaking of inversion symmetry. This is the appearance of spin orbit in the system. And here I will really summarize a lot of data. I will try to explain this in a few slides. So what we measure here is the magnetoconductance versus magnetic field. So the change in conductance at the interface versus magnetic field. And here we cross the phase diagram. So if we are here with minus 300 volts, we are in the very underdoped regime, very few carriers. And what we see a conductance which is increasing as you increase magnetic field, and the scale is E squared over pi h. What I'm showing here are very famous data from Bergman, who was studying at the time 2D conduction in magnesium. And if you take a pure magnesium film, you see this same effect, which is shown here. This is weak localization. And this weak localization is a quantum correction to the conductivity that you observe at low temperature, and which is due to interference, electronic interference around closed paths. And these interferences are leading to localization. Now, when you apply, yes?
It's a very different field scale. Yeah, the field scale wasn't, right? It's a very different field scale.
Yes, it's a different field scale. So the field scale is linked to the strength of the spin-orbit interaction. The field, the characteristic field strength is, okay, now, yes, I agree. I was looking at the minimum, but the minimum is this B spin orbit is telling you something about the strength of the spin orbit. Yeah, you're right. Field scale.
The magnetic length is going to be very, very short, so the whole weak localization is a bit, no?
It's L5.
Huh?
It also depends on L5, right? What is the
Yeah. So from this data, you can extract the spin orbit characteristic length, and you can extract the inelastic length from the analysis, which I will not discuss. But okay, let me go on, and I'll be back to this. Okay, so this weak localization, when you apply a magnetic field which is perpendicular to the plane, this magnetic field is breaking time reversal symmetry, and so you dephase the electron waves, and so you restore conductivity, and this is why the conductivity is increasing. And the characteristic scale for this is E squared over pi h. Now, what you see here is that when we increase the carrier density, the behavior is changing. First, you see a small dip, and then it's going up. And this is also what was observed here when gold was put on the surface of magnesium. And gold is a strong spin orbit scatterer, and this is called weak anti-localization, and this is a signature of a spin orbit interaction. And in fact, what we see, this is what you see here, so in this region of the phase diagram, we see this behavior. When you move here, you see this weak anti-localization behavior. And from this analysis, we can extract the spin orbit strengths. And let me just mention that there has been a lot of work here in Tel Aviv in the group of Yoram Dagam with Alek Palevsky on the same type of studies, but using a slightly different technique to extract the spin orbit strengths. Now, there is something which is important here. What we observe here is not an ionic or band spin orbit, but it's a spin orbit which is linked to the breaking of inversion symmetry that you find at the interface. This is a so-called Rashba type spin orbit. And the way to see this is to compare the spin orbit scattering time that you extract from analysis of this curve to the elastic scattering time. And if you have an ionic or band spin orbit, the spin orbit scattering time is proportional to the elastic scattering time. The more diffusion events you have, the more chances you have to lose your spin phase currents. But if it is a Rashba type spin orbit, the relation is a Dyakonov parallel relation, and tau SO goes as tau minus 1. And this is what you see here. So the spin orbit is important in the system, and its strength is increasing as you cross the phase diagram. And you see the scale, it's a few milli-electron volt, and this is much larger than the superconducting gap, which is 40 microelectron volt. And you also see that the doping range over which the spin orbit is taking off is very close to the doping range where we start to see superconductivity. And I will come back to this. What we believe here is that this doping range is the doping range where we start feeling or seeing the influence of the heavy bands. So what we believe is that this range is here where we start to feel or be very close to the XZYZ bands. From tunneling experiment. From TC with a rough estimate, but Manhart, I will show you, has made some tunneling experiment. Okay, I'm not mentioning this here in detail, but we have magneto-transport evidence, and several groups have been working on this to show that in this region of the phase diagram, this is where we start to, okay, now not everyone agrees or not all the experiments agree, but in this region we start to have multiband transport. For instance, in this paper, we looked at oscillation of the magnetoconductance in plane, and these oscillations we believe are linked to XZYZ bands, and they die when you leave the superconducting doping regime. And also, the measurements show that the two bands or the different bands have different mobilities. And let me also mention here the work of Charlie Lani in the Weissman, who has been working a lot on this. Okay, all this will be important now for the discussion of bulk and interface superconductivity. Okay, so now there's one thing which is very important, and many of you know this. Strontium titanate can be doped and is superconducting, bulk strontium titanate. And what you can do, you can replace strontium by lanthanum, titanium by niobium, or you can remove oxygen. And if you do this, the system is superconducting, and you see here results from 67. You see here TC is going up and TC is going down. So you see a dome, and you see that TC is about, max TC is about 0.3 K. So it looks very much like what we see at the interface. And so what I would like to do now with you is to try to compare the two systems. I should mention also here work from the group of Cameron Benya, more recent work in Paris, which shows that the dome is extending further here. Now, the difference with what I showed before is that here, since we are in the bulk, the N is a volume carrier density, so it's a number of carriers per unit volume, per cubic centimeter. And so we will have to make some translation. So this is the behavior of the bulk, and again, this is the volume carrier concentration. Okay, so the first thing to do is to translate the sheet carrier density we have to a 3D carrier density. Okay, in principle, it's very simple. You just have to divide by the thickness. Maybe a first thing to notice is that, and possibly a problem, is that in our system, the carrier density is not homogeneous. We have some kind of an exponential decay when you move away from the interface. But let's say as a first step, let's try to simply divide our N2D by D and see where we are in the phase diagram. So for the maximum TC, we find that our volume carrier density is here, and so we are reasonably well placed in the phase diagram. But the first thing we noticed is that when you remove carriers from our system with field effect, we know that we can change the carrier density maybe by a factor of 2 or 3, not more. Now here, it's a log scale. So what it means that the superconducting regime is somewhere here. So we're losing superconductivity more rapidly in at the interface. And I believe this is due to the electronic structure of the interface. As I mentioned, in the interface, we have this particular electronic structure. If you look at the bulk, and this is coming from the group of, from Dirk. Yes?
Didn't Cameron show that for oxygen doping, there is a separate dome than for niobium and lanthanum.
Yeah, yeah. So okay, I didn't discuss this. What Kamran Benya showed is that okay, here it's really a sketch, but here it is more complicated, and you see anomalies which he believes are linked to the filling of the different bands. And this is from also Shubnikov, the oscillations, where he could see at which opening. So you're right. The dome here is showing some structures. Yeah. So in the bulk, you see the electronic structure in the bands, but very quickly, as you fill, the system is finding heavy electrons. At the interface, because of this electronic reconstruction and confinement, the first bands are very light. And so the proposition is that these XY bands are leading to a very low TC. You know that TC goes as an exponential of the density of states, and a light band means a low density of states. And this is backed up by recent calculation from Davide Valentinis, using, by the way, Kamran Benya data to extract the coupling parameters. And it shows that as long as you're not touching this XZ, YZ band, TC is essentially 0. This is also in line with measurements of 110 structures. And this I will not really discuss in detail, 110 and 111 structures. But this is work coming from Barcelona, where they compare the behavior of O1, what I have been discussing, with 110 structures. In the 110 directions, you know, the planes are at 45 degrees. The orbitals are different, and the orbital ordering is different. And in this direction, the lowest orbital are not light ones. And you see here the TC behavior. This is what I was describing, and this is what they see in the 110 direction. So it could well be that at the interface, in the O1 direction, we observe superconductivity at higher doping because we have to fill these heavy bands. Okay, now another surprise is when we start to when we try to map this dome to the 3D dome. So what should we do? We should simply take the carrier density and divide by the thickness. But we have to check what the thickness is as one is crossing the phase diagram. So what we did this perpendicular and parallel field measurements as a function of doping. And this is what you see here. Okay, this is a little bit busy, but this is TC. This is the doping. So TC is here. You see the phase diagram. And for each of these points, we went through perpendicular and parallel field measurements. And the result is shown here. In green, this is the thickness versus doping, which is given here in conductance. So 10 nanometer, but you see here, as you go in the overdope regime, the thickness is increasing. And we know this for quite many years, but we only reproduced the data recently. So now what we have to do, for each of these dopings, we have to divide by the thickness. Okay, so what I do here, I zoom on this part of the phase diagram. This is the bulk TC, and we start from here, and we start adding carriers. So the thickness is constant. You add carriers, you reach maximum TC, you go a little bit beyond, and then the conducting layer is expanding, and is in fact expanding faster than the number of carriers you do. And so finally what you do a loop in the 3D phase diagram. So is this the reason why TC is going down? I don't know. But what is interesting is that the properties of samples here for the what we call underdoped and overdoped are completely different. If you look at the superconducting transitions, if you look at Magneto-transport, it's completely different. And clearly the good parameter is not the 3D carrier density, which is the same, but maybe more the mobility or the conductance. To make things a little more complicated, let me mention recent work in Stuttgart in the group of Johann Mannert. This is tunneling Harn I was just mentioning. So they succeeded performing tunneling experiments through lanthanum aluminate, and they could cross the phase diagram. And you see here the conductance versus voltage from which you can extract the superconducting gap. And you can do this across the phase diagram. So this is TC. Okay, this sharp drop here is due to the definition of TC. This is essentially the dome I was talking about. And if you start from here, so this is TC and this is a gap. So the gap is increasing as TC is increasing, everything is fine. But you see here now the very unusual behavior which is observed. The gap continues to increase as TC is going to 0. So the gap is not following TC. Yes, oh, I should speed up. Okay, so this is very unusual, and their explanation is that there could be a fluctuating superconducting region in this area, something which goes maybe in line with this, the fact that we have a lot of fluctuations on this side of the phase diagram. But anyway, if you take this delta, you can extract the mean field TC. And if you do this, then you find that the TC from tunneling would do this, from the underdoped to here, and then going like this. Now, if this is the correct TC, what I was telling you about these heavy and light bands is much less compelling, because now I cannot really explain this. Yes?
The phase diagram that you showed, I think I remember you showed T costalis taurus. Then when you extract TC, you extract it from midpoint of the transition. Then you're talking here about the gap TC, which is a kind of like the mean field TC. These are all very different quantities.
Yeah. Okay.
The costalis taurus TC is definitely not going to be the same as this TC.
Yeah. Okay. So you're completely right. I went too fast. The first phase diagram I showed you was a costalis taurus analysis TC. When I was comparing to bulk, we use the midpoint, which is more, say, a criterion which is in line with a mean field TC. So I should have said this. So this analysis we did here is with a mean field TC, and this is why I'm comparing this with the delta TC. So it's different from the first phase diagram you saw. Okay, so the short, let's say, we don't know yet what is the good answer here. Now, to finish with superconductivity, let me just mention one thing, which coming back to spin orbit. Because we have a strong spin orbit in the system, so in principle, superconductivity should be affected by spin orbit. The only thing I can mention here, and I should also mention the work here of the group of Johan Dagam, that we measure the paramagnetic limit, and they measure the parallel field, which go way beyond the paramagnetic limit. So this is a paramagnetic limit, this is a parallel upper critical field, and from work, I guess, from Stanford, from Mac Beasley, Clem at the time, there is a way, if you know this ratio between the paramagnetic limit and what you measure, there is a way to go back to the spin orbit scattering time, which is the one you would need because spin orbit can enhance this parallel field. And if you do this analysis, and we did it here, you find, okay, and I didn't show this graph, but this is a spin orbit scattering time versus gate voltage. This is what we get from transport, and this is what you would get from this analysis. So it could be that this enhanced parallel critical field is indeed linked to spin orbit. Okay, I should really speed up, so I wanted to show you some recent results on a system where we have less carriers. But let me just skip this. And I will just end by showing you some recent results. First thing I want to mention, okay, I'm just flashing some results to show you that this field is moving. We're able these days to get high mobility samples using different techniques. One way to do it is just to lower the gross temperatures. If you do this, you get lower carrier density and a high mobility. And we enter in the quantum regime, and we can see Shubnikov-Duas oscillations. You see here results from Harold's group in Stanford. You see here results from Geneva. And obviously, it's interesting to study these Shubnikov-Duas oscillations, which will give us some information on the electronic structure. Many people try to transfer this interface to other substrate. Not so easy. To this point, it's been very hard to keep the metallicity at low when transferring. This is work from the group of Changbo Meom. People have been trying to make multi-layers. It's quite difficult to make sure that every interface is conducting. In Geneva, now we are able to make bilayers with two superconducting systems. And one of the ideas I will not discuss here is to try coupling these superconducting layers and, for instance, see if there is any effect on fluctuations. There is great work on nanostructures following an idea of Jeremy Levy, who is really way ahead with this technique. And the idea is quite fascinating. What you can do, you can start with a layer thickness of LaO of 3 unit cells. If you remember, 3 unit cell is just below the threshold. So the system is insulating. But if you come with an atomic force microscope with a metallic tip, and you have contact, and you apply a bias, you can induce the conducting layer just under the tip. And this is stable. And doing this, you can write nanostructures. And I'm just showing here one example coming from Jeremy Levy group, where you see here conducting layers which are only 2 nanometer wide. You can make transistors, and there are interesting studies which go in the direction of mesoscopic physics. Let me also mention work here in Tel Aviv, very innovative work from Yoram Dagan group again, where they could make one-dimensional quantum wires. And I think there will be work on this at noon. Seebeck coefficient, thermopower, has been measured in the system with giant values and giant oscillations, which could reflect localized states that you have at the bottom of the band, maybe some of the missing electrons. And let me also mention that spin injection has been tried in the system. You see here results from Paris, where you use a cobalt electrode, you inject spins, and you measure the spin imbalance using the Hanley effect. The dream would be to control the spin polarization using the Rashba effect. But unfortunately, the lifetime are very short. And I've been mentioning the LaO-STO system, but other systems have been studied. Very interesting, lanthanum titanate instead of lanthanum aluminate. It's a MOT insulator here in Paris, here in Santa Barbara. Beautiful work in the group of Susan Stemmer. Okay, let me end now simply by coming back to my question. Will we use these oxide or oxide structures for future electronics? And I'm showing you now a slide with all the modesty which is necessary, comparing a transistor here, the 1947 Bell Lab, with a transistor made in Geneva in 2009. But I'm showing you this because just in a few years, in Stuttgart, the group of Joran Manner, they were able to make essentially 1 million transistors, which at room temperature have really textbook characteristics. So I don't think we will use this oxide electronics very soon, but it shows that standard techniques can be used to realize devices. And I really hope that we will be able to use the fascinating properties of these oxides in the future. And no conclusions, but I'm just mentioning a few reviews. And if you go to these reviews, you will see that I've been just talking about a few things, but there are very many possibilities with this system. So thank you very much for your attention.
Yes, please.
When you showed superconductivity versus as a function of magnetic field, it looks like there was a big drop, then it's saturated to some value at low temperature. Mm-hmm. What is the nature of the metallic phase? It doesn't happen with zero magnetic field?
Yeah, I don't know. I don't know. We are actually looking at these anomalies and to try to see if this is something which is systematic or not. But I have no answer. I don't know what this phase is.
So your results that this is not about superconductivity are very convincing, but I'm asking, does it matter if it's a polar catastrophe carriers or any high carrier density at the surface of STO would provide the same properties in superconductivity? Do you care about the LaO layer other than the source for electrons for the superconductivity?
Okay, so the LaO layers is producing a particular profile and a particular carrier density. We still have changes or from samples to sample, there is some randomness. We're not sure we understand exactly why we have this. So we have a profile which is, say, different from a homogeneous doping. Huh? Now, if we care, okay, I don't know what we are trying to do right now is really to make junctions to see if we see in the symmetry of the order parameter signature of spin orbit, because the spin orbit is due to this breaking of inversion symmetry. Now, you mentioned something which is important. I forgot to say, to me, the fact that the TC is the same for this very thin layer, then the bulk is not completely obvious. I think if you study very many systems, if you look at very many superconducting systems, as soon as you make a layer which is much thinner than the current length, TC is going down. Would you agree, Aaron?
Except for iron selenide.
Except for iron selenide, yes. Which was worth mentioning. Absolutely.
Also,
Yeah, except.
if you make it thin, TC increases.
Yeah, that's strange.
Aluminium? Okay.
Yeah,
Okay.
strange.
Maybe one last question because we're a little late.
So, just something that occurred to me. If you gate your strontium titanate in order to use carriers in the conducting layer at the interface, I assume that it's not just there, so there is some grading in terms of the, so adjacent to the superconducting layer, there is a layer which is not a graded layer which is not superconducting but kind of metallic, which by proximity should affect the superconductivity in that more robust superconducting layer, and can do either way, but most probably will decrease your TC. That's definitely a mechanism that can affect your TC.
Yeah. I think you're absolutely right. I mean, this gating, we're also studying now top-gated versus back-gated because the effect is not the same. You're right with these normal carriers. One thing I'm not sure of is if the XY electrons are really superconducting. If they're not superconducting, it may explain some of the result that Bina got at the time in Stanford, where the superfluid density is very low. In Catherine Moller group, but I'm not sure. So this question of how much superfluid electrons we have, I think is a very important one. But right now, with the tools we have, it's hard to answer this question.
Okay, let's thank
you very much.
Jean-Marc again.
Thank you.